Hey guys, Greaves here. Let's take a look at review 18. Okay, all right. So, these are problems that I have for you, and hopefully this one should seem a little familiar. We did this one in class or an exam. Okay, so toy car starts at A, it goes down the hill, shoots off at B. Okay, so let's take a look. Suppose the toy car is released from rest at point A, VA 0. After the car leaves the track and reaches its highest point in its trajectory, will it be at a different height than it was at point A? Well, okay, so I kind of looking at this as, hey, is it going to be at a different height than A? And the answer is, yeah, it's going to be at a different height than A. Why is that? Well, first of all, let's ask, will it ever make its way back up to A? Well, the answer is no. It can never make its way back up to this height here, whatever that may be. Why is that? Because to make it back up to this point here, all of the kinetic energy here, right? Potential, right? So here's potential. It zips down to kinetic, right? All of that kinetic at the bottom, right? All of it, which was the potential up here, right? Would have to be converted. All of it would be converted to potential to get here. But look what happens here. When it leaves B, right, at an angle, doesn't it have some velocity in the horizontal? Right? So if it has some velocity in the horizontal, what that means is some of the energy, right, is still in kinetic. So it's never going to have enough information. It's never going to have enough energy to make it back up to A. So what's going to happen? Yeah, it's at a different height. Yes. Why? Because some of the energy is in kinetic energy horizontal. So there's some energy, right, horizontal. Okay, so that's one. Right? Might be a more elegant way to express that, right? Determine the speed of the car when it's at its highest point in the trajectory. Okay, so what is the speed of the car at the highest point in the trajectory? Okay, so it's going to go off like this, and it's going to kind of do something like that, right? So what is the speed? Like we said, we had some velocity, right? So what is the speed, right, in the horizontal, right? So at this point, right, it leaves, let me do it over here. At this point, it's going to leave with some velocity, right? That's theta. So it's going to have some, that's really going to be B, right? Theta B. So it's going to have a velocity B in the vertical, sine theta, and it's going to have some velocity B in the horizontal, cosine theta, right? So this, right, is going to be my velocity, right, at when it leaves the track, okay? Or I should say, not when it leaves the track, my bad. At the highest point, because this VB, right, which is V cosine theta, is constant throughout, and that's the only velocity that's going to have right there. Okay, so that's going to be VB cosine theta. All right, so next part of this problem, right? B. Suppose the toy car is given an initial push so that it's non-zero. Determine the speed AV at the top, right? What's the speed that it must be going, right, to make it to the top of this, right, to make it back over here, right, because it's still going to be going this way as well. So what's the speed that it must be given, right? So how would I do this, right? I'm going to do energy. So K is equal to K, right? K over here. So what do I have? 1/2 mVA squared is equal to 1/2 mv, whatever this velocity is squared, right? So the m's go away, m's go away, right? So it looks like, what velocity am I going to have right here? When it makes it back up here, the only velocity that I'm going to have is mvb cosine theta. That goes away, that goes away. By the way, it's squared, so I can take the square root, so VA has to be equal to VB cosine theta, right? So that's the speed that I must give this guy to make it back up there. Okay, so that's 18. 18.1. Okay, so let's take a look at 18.2. Okay, so I have this situation where A and B are going to smash into each other elastically, right? Elastically. Kind of a weird problem here, right? What it's saying is VA bumps into VB. By the way, since it's inelastic, this guy is going to have the same exact speed over here, okay? It's going to go around the loop, right? Come up here to some height, okay? So derive an equation for the height h in terms of m, r, v top, and g as appropriate. Okay, so what type of energy am I going to have over here? So let's do this over here, right? So what type of energy am I going to have at the top of that loop? K, right, plus U is equal to U. Why is that? Okay, so look over here. It's still in the loop-de-loop. So it's still, right, here it's all kinetic. Goes here, kinetic. Starts converting some of the kinetic to potential, but I still have some kinetic as well. So at the top of the loop, V top, kinetic, plus whatever height this is going to be, 2R, right? That's the energy that's at the top of the loop. Kinetic plus kinetic, kinetic plus potential, loop all the way around, and then it's going to convert all that to potential over here, right? So what I have is 1/2 mv top, I'm going to call that just T squared, plus mg. Now look, right, look, here I have, this is the radius r, which means I'm going to have a height of 2r, right? mg 2r is equal to mgh. All right, we can do some slashing and burning. M goes away, M goes away, M goes away. So what can I do here? 1/2 vt squared plus g2r is equal to, so I guess I'm going to do a g there, I'm going to do a g there, that goes away, that goes away. So v top squared 2g plus 2r, so there's my equation. And not the most elegant way to do one, but that's the equation right there, okay? So it's deriving that equation. Suppose that V1 of block A is doubled. So I'm going to double this V. Will the final height of block A be greater than, less than, or equal to? All right, so here is a typical, what I would consider to be, you know, I said simple numbers, that other teachers said factor of change, whatever you like, right? So what happens if I double my initial velocity? So K is going to be equal to U. So how do I handle these problems? Solve for the variable that I want to change, or I want to see what happens to, sub in my ones for the things that change. So 1/2 mv squared is going to be equal to mgh. M's go away. I'm solving for h, right? So v squared 2g is equal to h. Okay, so I want to know what happens when I double v, what happens to h, all right? So I'm going to make that double. We're going to say everything's a 1, right? That's how I do this, right? So that's a 1, that's a 1, square that. So that's my original. Let's double. So I'm doubling 1. 2 squared, that's a 1, equals h. If I double my velocity, my height is going to be 4 times, right? So the answer to this guy is greater than h, less than it, greater than. As a matter of fact, it's 4 times. Okay, so that's that guy there. All right, so now, briefly explain, you do that with the math there, right? So next problem, okay? So now, we got this one, let's just read, right? So blocks A and B, both mass m, are moved at a different frictionless track as shown above. Let A be the minimum speed, right, that the block A travels such that B makes it to the top of the track, right? So VA, right, is the minimum speed needed to get B to get up there once I have my inelastic collision. Is that okay? So, etc. Block A is then replaced by block C, which is 2 times bigger, as shown. Block C makes a completely elastic collision. That means these two guys are going to stick together, right? Find the speed VC, right, that it must travel such that these two make it up here, and I need to solve in terms of VA. Okay, so how do I handle this question here? All right, so I need this in really terms of VA. So I looked at it, okay, so hopefully you understand that, right? VA and VC must be the same, right? VA, or I should say VA and VBC must be the same. Why is that? Well, let's take a look. Let's see if I can reason that out with energy. So U is equal to K, and I'm just looking for block in the first scenario, this guy right here, okay? So we're just doing the first scenario. So I need, what is the minimum speed, right? So 1/2 mva squared is equal to mgh. Let's take a look at BC, right? Let's take a look at what happens with 1/2 mvbc squared is equal to mgh. Now remember, I'm trying to compare the speed of A to the speed of BC, okay? Now, I'm just doing this to show you that VA is going to be equal to VBC because I need to solve things in terms of VA. So what can I do? That can go away, that can go away. Let's solve for H. So solving for H, VA squared is 2G, right? That's H. How about this guy over here? That goes away, that goes away. VBC squared is 2G is equal to H. I'm going to set these two guys equal to each other. So VA squared is going to be equal to what? VB squared. That goes away, that goes away. I can take the square root. So lo and behold, speed of A, right? The minimum speed of A to get to the top needs to be the same exact speed that VBC needs to be. Hopefully you recognize that before, but if not, I'm showing it to you right now. Okay? So now, with the knowledge that VA is equal to VB, C that is, right? How can I solve for the minimum speed? This is now we're going to use momentum, right? So in this particular case, here's my track, right? These two guys now are going to stick together, so that's going to be 3m, right? So before, what do I have? P before is equal to P after, right? So P before, P after. Before, right, I just had VC, right? 2m, right? B was at rest, right? So that's going to be 0 is equal to, now they're going to smash together. What do I have? 3m VBC. Okay, so what do I have? That goes away, that goes away. I know that BC is equal to VA, right? So I'm going to VC 2 is equal to 3 VA, right? So we're going to divide by 2, we're going to divide by 2, and we're going to get VC is going to be equal to 3/2 VA. So there is the minimum speed for VC that I need in terms of VA to get this block to reach it to the top. Okay, so that's 18.